Welcome to our lesson. Today we continue with our lesson on how to write circuits in Noir. So just like we've done before, it will be practical lesson. So I will be doing it practically. And our focus today will be on automation of ZK proof workflow with the Noir. So we intend that when you write your ZK proof, the generation of the key, the generation of the proof and the verification will be done automatically instead of somebody having to put the commands from time to time. Just input your commands as you write. As you write, you input your commands, and then you just run, and then it automatically runs instead of putting a command another time. So you just put the command at the time of writing your circuit. So basically that is what we'll be doing, but our objectives by the end of this lesson, we will have explored modular project design in zero knowledge proof development. That is what we expect, that the learner should be able to explore modular project design in zero knowledge proof development. And then at the end of the lesson, you also are supposed to have understood how to structure and script proof pipelines. That is what I mean by this. By the end of the lesson, you need to know how to write those automatic proofs. How that is the likes of build.ish. Build.ish. Need to know how to write it, and you need to know the structure. How do they begin from scripts? What is the next one, and what's the next one, and so on, and as you move down. So that's what I mean by the structure. Which one comes first, followed by which one, and then followed by which one. That's what I mean by that. And then you need to know, at the end of the lesson, you need to know how to implement so those are the objectives. And we also expect that at the end of the lesson, you'll have gained experience on how to run complete proof workflow at the end of the lesson. So that means everything will be hands-on, so that as I do, you also do the same thing, move together from the beginning to the end. Now, so what is the essence of making it automatic, the proofs, automating the proofs? What is the rationale? Why should we be doing this? Now, one thing I've already mentioned, that we do not need to be repeating the commands every time we want to run the proof, that you have to, again, provide the command every time. So instead of doing that, just provide the command at the time of writing the circuit, provide the command so that your part will just be running. Just tell it to run, and then it runs instead of writing the command. And so the problem of writing the command is that sometimes there might be errors, that you might input a wrong command at some point. So why can't you just input the right command at the beginning, and then that command remains there, and then you'll be using it. So Automating also helps reliability and reproducibility. That means if anybody was again to run your code, this person should get the same results like the one you get when you do it. Because you're using the same command that you had already put, so the person is just running. So if the person runs, you should get the same results as the ones you got. So that we don't have the one circuit giving us different uh, results or outputs depending on who is running it. So again, that is the advantage of automating. Now, for new developers, it also helps new developers. It reduces the onboarding time. And then another one is that it's ideal for integrating with the CI and CD pipelines and front-end deployments. So those are the advantages of automating. And so that is why we should therefore automate. Now, this is just a reminder of what we had already mentioned, the advantages of Noir, what Noir is, and why we are using it. So I'll not repeat it, but you can see Noir enables writing ZK circuits in a readable Rust-like syntax. So these are the things we've already mentioned in our earlier lessons. Again, I'll not repeat because we have enough to do today in terms of practice. Now, so straight away, we'll go to our WSL and we want to create a new project. And then after creating a new project, okay, this is where our projects are kept. For me, it's Rust programs. Rust programs. That is where I keep my projects. So I have used this so that you go to where you normally store your projects. For me, I'll be going to Rust programs. Then now go new the name of your project. So let's call it today, let's call it ZK Autoproof. And then after that, we'll CD. That means we enter inside the project and then make a new directory. And this new directory, we call it scripts. We shall just call it scripts. There's no need of verifier input. You can just say make new directory scripts and then enter. And then we will code, write code, a space, and then a dot, and then enter. So that it now opens for us the Visual Studio, the Visual Code, so that we begin writing. So therefore, I will now unshare this and share my WSL just for this step, these steps that we do it together. Because we said this is supposed to be a practical lesson. That at the end of the day, we all know what we are supposed to be doing. Let me share my Visual Studio. So we said we go to where we store our programs, where we store our projects. For me, I store at Rust projects, no programs. So you CD that, you get inside, and then we now want to create a new project. We said we'll call it ZK or it's a Nago new. Then the name of the project, we said we call it ZK automatic. Automatic proofs. Okay, so that is the name of our project. Let me just copy it and then enter. Oh, my Nago has a problem, but I'll just fix it. It's not in the right path. It's not in the right path. So if I take it back to the right path, let me just come out and then give it this command to take it the right path. It's now in the right path. I can confirm by asking for the version. If it gives me the version, it means it's in the right path. But if it's not, then it will not give me the version. It has given the right version. Let me again repeat the process. CD Rust programs. Rust programs. Okay. And then Nago new. Nago new. The name of our project is ZK automatic groups. Again, let me just copy it. I'm copying it because we will then, after this, we'll CD it. So you can see the project has been successfully created and is located inside my Rust programs and is called ZK automatic proofs. Now, so we now enter that project. That's why I was copying. So we enter, we do CD, the name of our project, and enter. So we are inside. So while inside, we can make a directory, and we said that directory called scripts. Okay, let's open this project and now begin editing. So I'll now unshare what I'm sharing. I'll unshare this and then now share what I'm seeing from my end because the visual code is now open on my end. So I want you to see, and I hope you're at the same point and yours is also open. You can compare with yours. So mine is here. You can see where I'm pointing. ZK automatic proof, that is the name of the project, and the scripts here, the scripts, and then under it we have SRC, and inside SRC we have the main.nr, and this is the default. This is the default main.nr, and we shall replace it with the one we'll be working on. We have the Nago Tomil is here. So, but automating, what the commands we'll be using to automate would be putting them inside here. Putting them inside here. So let's, for instance, when you right click here, you can input a command, I just right-click scripts. For instance, I can want to input build.sh, and then you input the command. So we'll be inputting the command there. Inputting our command, we'll be inputting it here. So for instance, if I want to input a command for key generation, I just right-click on the script and then press new file, and then I have keygen.sh, and then enter, gives me where to write the command for key generation. So this is what we'll be doing. So let's continue with our notes, and then once we reach here, we'll come back and continue with the process of automating our circuit, our key generation. So basically, that is what we'll be doing, so to automate. Now, so inside the scripts, we'll be having I've given an example, build.she, the prove, the verify, the key generation. So each of these scripts corresponds to a ZK workflow. It enables quick rebuilds or tests, quick test runs with a single command. So the command will just be like, for instance, this build.sh. When you just say build.sh, you expect that the test runs. And when you say verify, the test will run and then verify. When you say keygen.sh, it runs and then generates the key. So that's what we'll be doing. But just that is a quick command. The thing is, I've shown you how we'll be in building our commands. That is why we'll be putting our commands. And so you just come to the terminal now and say keygen.sh, and then it runs and generates the key. Now, I've written here something, think like a ZK engineer. So that means treat each stage, compiling, key generation. Of course, we'll be doing Nago compile, Nago execute. Then we do key generation, we do the proving. So for us to think as a ZK engineer, it means we have to think that at each stage should act like a predictable function. It will take inputs and then produce outputs. So we already gave it inputs, and then the output should be the same. As I had already said, anybody coming in and doing the same command should be able to get the same output like the one you got. Your scripts become versioned, reproducible. And the word is reproducible. That means they will always produce the same results. So I'll explain that. I've said, write your setup scripts so that they are tracked with JIT and give consistent results. This makes them reliable and reusable. So that is how we are supposed to be thinking. When we write our scripts, they must be reproducible. They must be versioned. They should give consistent results so that it doesn't give us one result this time And then next time it gives a different result. Then the other thing is that we should automate proof generation and verification by integrating the scripts into CI and or CD pipelines. So of course, that is what we'll be doing today. It's part of our today's lesson. Automate proof generation, automate verification, and so on. Now, so what I want to do this time, I want us to write a circuit for that would assist a prover to verify or to prove to the verifier that his age is between 18 and 60. And we had looked at this example earlier. So we write that circuit. And then after writing this circuit, we want to automate a proof generation, proof verification, and so on. So that is what we'll be doing. So, but the circuit, you already have it. You already have the circuit. So I'll just look for the circuit and then we paste it. Because it's a circuit, the same circuit we've been looking at, we looked at in our last lesson. So let me again share my visual code so that we now begin the process of automating our proofs. So first of all, I have to share this. Now, so what I'll do, I'll create all the scripts. We had then after that we will then input the commands together. So we had created build.sh, then keygen.sh. Let's also create proof.sh. So this is the command where we shall input our command for proof generation. Build.sh will be doing the entire thing. First of all, to begin by Nago compile, do proof key generation. And of course, it will be calling on this. It calls on the key gen. The key gens it, and then it picks from there. So it will be calling on other scripts to perform their roles, and then it picks from there. So in short, it will be doing the entire thing, the complete task. Now, so we have these 3 scripts. Let's add one for verification. Verify dot sh. There's so many because we also want one that will be doing the solidity solidity verifier. We also want one that will be doing that. So we will be adding them as time goes by. So let's input the command for, first of all, before that, let's input our circuit. Let's input our circuit. So our circuit is here. So this is the circuit we've been looking at. and we just checking whether somebody is between 18 and 60 without this person revealing the exact age. So it's just telling us that it's between this age. Now, every time you write a circuit, then you're required to do Nago compile. I'm looking for my terminal. Okay. Does that make sense? Okay, that is okay now. So my terminal is there. Now, so let's do Nago compile and just see whether the whole thing is okay. It's okay. We can also do Nago tests. Nago tests. Although it's not mandatory. What we require is Nago execute. But for us to do Nago execute, first of all, we're required to do we're required to have proof. We're required to have prover.toml. Prover.toml. Prover.toml, you can just say age equals to 35. Then let's now try Nago execute and see whether it runs. Oh, it says it expects age and is not seeing it. So I think the problem we wrote with the capital, our age is supposed to be small letter. Yes, that is okay. Let's now again try Nago execute. Yes, it expected age small letter, but we had written with capital letter. So that is okay. That's okay. Let's begin again. Let's begin again and see if everything is okay. Nago compile. Nago test. Nago execute. Good. We are okay up to there. So what then follows is I want to input our commands for key generation, build.sh, and so on, and then make our scripts executable. Once you make the scripts executable, you can now proceed and run the commands. Now, so I'll paste the command for key generation. This command, we had used it earlier. This time we just automating it. We just want it to be automatic. So that is a command we've seen before. the command we've used. This is the command for key generation, BB, write a verification key, and so on. So we want it to be written inside the target. But the only thing I want to change is this. The title of our project is ZK automatic. Proof. So that is, we need to be keen. We need to be keen. So that we will then generate ZK automatic proof.json because we will require it, and it must be created inside target. Target is here. We got it when we compiled, when we did Nago compile, a target came in and it has these two. You can see we have ZK automatic proofs, supposed to be proofs. That's the name of our project. Yeah, proofs, not proof. So for the key to be generated, verification key to be generated, this is very vital. This one is important. It will then be used. So we have, this is the command for key generation. We are doing it using KCAC. Now, let me also bring the command for proof, generating the proof. That again is a command we've seen and we've used. So for generating the proof, the command we had used this command earlier. This BB proof scheme ultra honk. Now you can do it ultra honk or you can do it Oracle. In our case, I want us to do it Oracle hash kekak. So even deleting this one has no problem. You can delete it, but let's just keep it. Now, again, as we did for the key generation, I want to copy the name of our project and then replace the one I'm seeing here as Edge. Replace it by the name of our project. Replace this also with the name of our project. But the proof will be in the proof directory. So when I run this, there'll be a proof directory, and inside this proof directory, you shall see a proof, and there'll be this saying that the proof has been created inside a proof directory. Okay, let's again get the command for build. The command for build.sh. Now this is the command. Now what build.sh will be doing is the whole thing. It will be generating the proof. So just calls on the proof, on the proof.sh to generate the proof. And then it will also be generating verification key by calling on the keygen. And then it will be doing a verification of the proof by calling on the verify. And then it will be doing the solidity export verifier by calling on this export solidity verifier, and so on. So those are the things it will be doing. So the ones we've not added, the command is the verify. So let me again get the command for verify. And the command for verify, again, we had seen it earlier when we were doing, when we began this. We saw the command for verification. This is the command. And I said we are dealing with the kekak. So that is why you don't see the honk here. Otherwise, if I were not using kekak, I would have added the honk. Now this one has nothing to edit, it's just okay, the way it is. We have this, we have that, we have this. So build.sh cannot work now because it only has, we only have the proof, we have the keygen, we have the verify, we don't have the solidity verifier. So if you run it, it will not run because we'll be calling on the solidity verifier, and the solidity verifier is not among these. So we need to create solidity verifier so that when it calls on it, it finds it. But if it doesn't find it, then there'll be an error. It will not run properly. It will give us an error. So we want to create a script called export solidity verifier.sh. And then we want to put the command. The command for that is here. And again, we had used it earlier. We had used this command earlier. Now, so there are so many scripts we can add. There are so many scripts we can add depending on what we want. For instance, you can also add the script for clearing the target, delete the target. You can also add one for testing so that it does the tests automatically. So let's even, in fact, let's add the one for doing the tests so that we are doing the tests for, you remember that our circuit, we're supposed to test that somebody is within 18 and 60 years. So you can test every age. You can test 17, 18, and so on. That's what I mean by the test.sh. So it does test all the ages. So that one you just say new test.sh. And this is the command. So you can see it will be testing all the ages. So like 17 is not between 18 and 60. So we expect it to fail. So when you run that, it must fail. 17 will have to fail. 18 will pass. 35 will pass. But 16 will fail because again, it's outside. The range. Our range is 18 to 60. So anything outside that is supposed to fail. So test will be doing that. It will be testing. You can change the edges and input any other edge you want to test, and you see how it runs. So the last script I want to add is the clean. I had already talked about this. This is the one that will be cleaning whenever we want to do away with the target, with the entire content inside the target. We'll be using this to clean it. So just call clean .sh. Now, so having added all the scripts required, we want to ensure that they're executable. So for you to ensure that they're executable, we can inside this root ZK automatic proofs, we can run the command chmod plus x scripts and so on. This one makes all the scripts executable. Now, so I now want us to run the key verification. So let's enter scripts, cd scripts, cd scripts. Inside that, so let's do dot backslash verify dot sh and see what we get. Okay, so it's unable to open the target proof directory. Okay. Let's do this. Let's first of all create the proof. We have not created the proof, so that I think that is where should have begun. So dot backslash proof dot sh. Good. Now this one is successfully run. We've compiled. You can see what it did. Compiled the circuit, executing the circuit to generate the witness. And then ZK automatic proof. The circuit witness successfully solved. Then witness has been saved. And where is it saved? It's saved inside a target and is called ZK automatic proofs.gz. And then we have creating the proof directory. Let's just come and see whether it's there. Just come to the circuit. Yes, you can see we have a proof directory. And inside the proof directory, we have the proof. So this time, I think we should be able now to verify. You can see the proof has been created inside the target proof directory. Okay, let's verify. So again, or we can even generate the key. Let's generate the key. Keygen.sh. Keygen.sh. Then it says generating verification key. The scheme is ultra hong finalized. Circuit size is this. Verification key saved to target BK. So when you come to target, you can see BK. That's where verification key is. That's why it has been saved. So let's verify. Just say dot backslash verify dot sh. So again, it's unable to open this target. Okay. Yes. What if we were just to do it directly? What will it say? Let's just see. If you were to just of course, we're supposed to do it using that command, but I'm wondering why it's not behaving. If we were to do directly to run, why is it not running? Okay. That was verify. Okay, we can also run it inside inside here, but if you are to run it inside here, any of them can be run from the main root. But if you are to do that, you must begin by dot / scripts, then say verify .sh. Let's see whether it will accept here. Here it accepts. It accepts verifying the proof. Let's go back. See these scripts. I don't understand why it should not accept here. See these scripts. Then dot / verify .sh. That it doesn't. So it wants us to run it from the main root. Wants us to run it from the main root. There's no problem. Let's go back here, the main root. And the main root you must, this is the command, if you are to run it from the main root, any of those can be run from the main root, but then the command should be, for instance, if you want the proof one, if you want to prove, you do it dot / scripts prove .sh. It will still run. It will still run. So you can run any of them from the main root. There's no problem. I just wanted to go up to script. Now let's do build. Let's do build. So I'll just be editing this. I want to run all of them from the main root. So I just write here build .sh. It's done. It was not successful. Oh, cannot create the on-chain verifier.sol. Okay. Now, so what we're supposed to do, we're supposed to create a directory and call it on-chain. Supposed to create a directory, make directory, and call it on-chain. So this is the directory called on-chain. So we want to, inside that, we could even, in fact, we could move this verifier.sol, but instead of moving, let's create a file here and call it verifier.sol, because that is what build is looking for. And then copy what is inside this verifier.sol, copy it and paste it inside this new verifier.sol that is inside on-chain, because the build.sh is looking for the verifier.sol inside on-chain. That's what it's saying, cannot create a regular file on-chain verified.sol because the verified.sol, the on-chain directory does not exist because the on-chain directory does not exist. So let's again run this command and see what happens. So I hope this time it is successful. Yes, it is. It is successful. And what has it done? Step one, it has proved that somebody's that 5 years compiling the circuit, executing, and so on. So that 5 years is within the range, the required range. And so all this is what it has done. Step two, it has generated verification key. So it only generates if it's missing. And then verifies the proof. And then exports Solidity verifier. So it's doing all those, but it's not doing it alone. It's calling on these others, on these other scripts to do their role. Then it does up to verifier copied to on-chain. So in fact, what this means, if we were to delete this, let's just delete this and see what happens. Will it create? So we have deleted the verifier.sol that was inside on-chain. And we run this command again, build scripts dot /build.sh. Let's see whether it will create verifier.sol inside that. Let's now come here. You can see it has created it. It has created verifier.sol. And this is a command we gave it. This is a command we gave it to create, to copy the verifier.sol to verifier.sol on chain. So the verifier.sol is here. When we ran export Solidity, it was created. Now, once it's created, the build comes and copies it on chain. It copies it here. In fact, this is the command, copy. Copy target and slash verifier.sol. So that means copy the verifier.sol that is inside the target, copy it to on-chain verifier.sol. This is the command. So it does that. So at first, when we ran it, it did not run because we did not have a directory called on-chain. So it had nowhere to copy this verifier.sol to, because it has the command to copy it. It has the command, that command, you can remove that command if you don't want. If you don't want it to copy, you can remove the command. Okay. The other test is the test.sh. This one wanted to test several edges and see whether they are within the range of 18 to 60. So those that are not within that range, it must tell us. All tests have been completed. So let's just go through and see which ones were found to be within the range and which ones were found not to be within the range. So I'm looking for where it is. Okay, to prevent us from reading so many things, let's just clear our terminal and then run it. Where we have, because it was a very long thing, depending on how many tests you wanted to run. So it would be very long. So, but now we only have the results only. It began by testing age 35. And from my test, when I wrote the test, I expected that 5 to pass because it's within that range, 18 to 60. But let's see what it found. So it began a full build pipeline. Step one, it did the proving and then compiling the circuit, then executing the circuit to generate a witness. It went through all that and then found that, okay, this was within the range. So the proof was generated and then saved here. And then step two, it generated a verification key for the same. Verification key was, of course, it was using key gen. And then it also verified the proof. Because all this happened because the edge under question was within the range. But if the edge would not have been within the range, we don't expect to do all this. Then exported solidity verifier and so on. Then the verifier was exported to target. Now from there, it came and tested 18 years. So that again, 18 is within the range. So it went through all those steps as above. But then here we have 17 years. 17 is not within the range. So it began building the pipeline, proving that 17, whether 17 was there, and then it found it was not, it failed. So this failed. So you can see this is a very short thing. It's not like the rest. So it did not have to go through all those steps because when it just began, discovered this thing is not within the required range. So the test fails. It also tested the 61, and as expected, again, this one failed. Very short thing here. Did not go through all the steps because this was 61 was not within the required range. But 60 here, you can see 60 is within the range. So we expect that it goes through all those steps up to solidity verifier. Goes through all those steps. So do we run exports? Solidity, let's again do it. Export solidity. Verifier .sh. Okay, it's done. So you can see we've automated our proofs, and so that means anybody wanting to do the same would get the same results as we got, because the person gets what we have and just runs the commands. Just does, for instance, a dot backslash scripts backslash export solidity verifier, then gets the same thing. This person is not required to write the command. Of course, we already have the command in build. We already have the command in build. We already gave it. So the person just does scripts, export, solidity, verify. So it's expected to get the same results as we got. So if he does build.sh, again, still get the same result. If it does verify.sh, it gets the same result. Not expect to write the command here. Previously, we were writing the command at this terminal. But as I said, making it automatic helps us because we may not have errors going forward, because once you input the command, it's that command that will always be used. So you are not supposed to again come and run the same command in the terminal. Now, the one we didn't use is this clean. I decided clean deletes the target. Let's just see how it does that. Let's see, clean .sh. You can see we have no target. We have no target. So for us to have target, again, we have to begin from the scratch. You have to do nago compile. Okay, we have now the target. The target is now here, but it no longer has what it had. So let's now do nago execute. And then now generate the proof. So you see what the target has now. The target has these three things. But now when we generate the proof, we get another thing, the directory, a proof directory, and inside that we have the proof. You can see we have the proof directory. Now inside we have the proof. Now this is the third thing we get inside the target. Now, having generated the proof, let's generate the key. Let's generate the key. So we're just using the same command, keygen.sh. We have the key has been generated inside the target. Now you have verification key inside the target. That is, you remember we had only these two at the beginning, but now we have the proof directory. Inside we have the proof. Then we also have the verification key. Let's now verify. Okay, we are verified. Let's build. Build is we're just doing what we've already done. What those commands above have done is what build will be doing. The only extra thing that it will now be copying from. Okay, before we do that, we need to run the solidity verifier, solidity export, to give us .sol, verify.sol. And let's try before that and see what happens. Oh, it created it. It created it here. Verify.sol. Then after creating it, it copied it on chain. So it did the two. Created and then copied. And I think that is a command we had given it. Let's just check the command I had given it. Okay, I'd said export solidity verifier. So it did this. It did this. It did what the export solidity was to do because it has the command. It has the command for exporting solidity verifier. Then after that, it then copied it to on-chain. Okay, that is how we automate. That's how we automate our proof generation and the verification. So for the sake of just making our notes complete, maybe you have already explained most of these things, but you can just go through now through the notes. These are the notes. And then you compare with what we've explained in our video so that we have complete notes and for better understanding. So you can see these are the commands we've been using. Scripts dot, we began with the dot, then backslash scripts, backslash verify dot sh. These are the commands we've been using. And all these I've explained in our video. So you're able to write your own circuit and try to automate the proof generation, verification, and all those, even key generation and so on. So at your own time as part of practice. Thank you.